and hosting this, so thank you for presenting this. And
the good things that we got is we can show movie. So I'm bringing up a movie as a first example of the movie can be orienting on the location as you want it and show it. And then suppose a moment, the movie will show you particles in the atmosphere, what we call the aerosol. So if I let it go and then I make some comments, I can interactively go over my own country, Italy, looking at the Sahara desert, and you can see the red is the dust, red and orange is the dust going in the atmosphere. Then if I move away, going into the Southern Ocean, you can see a lot of dust. It becomes white. It's the optical thickness of the particle, so it becomes white. Is really the maximum the maximum absorption of light for the particle. And then if I go to the southern hemisphere, the white and is the blue is the sea salt, and you can see the sea salt going into the weather system. And also we get gray, the sulfate, and green is carbon, both organic and black carbon. So the reason why I'm showing this is when we have environmental data set which are global, we can plot it, and we probably have seen some of this movie on a flat screen. But the beauty of having it on the sphere, I can locate around and identify a feature very easily. And the one I like particularly is the view from the southern hemisphere, where you can see the weather system. I'm a meteorologist, so I'm attracted to any weather system on a map. But interesting, if you look at the global nature of the dust from the Sahara, which is going into the atmosphere, moving with the wind, and easily spreading all around. And we will talk about the time scale on which this particle moves, and they have an enormous impact on the radiation budget. You know, aerosols are actually the most important, one of the cooling, the way you can cool the planet, and so there is a very study from the research. But I don't want to go into the research of aerosol, I just want to give you a feeling of how you can do. So the page is set up with some information, and then you can interact with the movie in that way. So I'll go out and give us some background information and go back to show some application. So the talk will span, if I go back to the room, will span example from the atmosphere and ocean, and then I'll pass it to Glenn doing some socioeconomic example from socioeconomic data set, how you can look at a movie, how to upload your own movie, and at the end we're also talking about how you can make up your own, how to use this utility for your own course. So I got here the kind of front page to acknowledge that people have already mentioned, and the fact that we've been sponsored by the educational grant from the ESI and from the Autumn Fund. And whatever I'm going to show you interactively comes from this URL that I put over here, which is still in the testing phase. So this is one of our first talks, so I hope everything goes well. So we've used it a lot for courses at MIT and also for for example, other educational activity, like the freshman pre-orientation. But we also use it in outreach. And here I have two. It's a great way of getting people involved. And you can see me, and the top figure here in the photo is me in Lobby 10 in front of Killian Court, just showing trajectory of balloons, solar balloon traveling with the wind in the atmosphere. We are actually releasing a solar balloon in Killian Court, and we were using the interface just to show people where this balloon could go if you let them go free in the atmosphere. And Glenn is here. This was part of the Cambridge Science Festival. Glenn instead is down here showing some data to students from the UN ambassador. They were visiting MIT, and they were part of a program for sustainable development. And we also using research for a project sponsored by the ESI on plastic in the ocean, and I'll mention something about that a little bit later. Because I was Professor Tom Mason and Clint Bureau and Hill are involved in this program. So if I go, the part of my talk is mainly related to examples from the atmosphere, and I will give you an example related to how I can display effectively field both from the atmosphere and ocean, but also how I can interact with the data. So we are all used to see display, but we want to be sure that we can interact with the data and show some application. So the example that I'm going to do for the climatology are data from the atmosphere on long-term means and ocean also mean fields. But the interface that we developed treats the two fluids in the same way. So you can see the kind of connection between the atmosphere and the ocean. So we try to emphasize that the two fluids are rotating planet and the connection between the two. So to go back to this, I'm going to show the example. I'm going to start with the climatology of the atmosphere. And what I'm bringing up here, as you notice, I have the sphere on this side where I'm plotting the potential temperature, at level 1000, so the bottom of the level. So you probably are surprised and say, why she plotted potential temperature? It's a big word. We use meteorologists, I like potential temperature. But I can switch and change it and say, the temperature that you have used, the air temperature in centigrade. So this, if you look at the globe, this is January, and it's a long-term mean, so a mean of more than 30 years. And it's showing a very cold land mass. We have a feeling of that cold air coming down tonight. And a warm equator, it's January. And I can do a section. So if I click here, you notice I have the green line, a north-south section. And on the side here, I have a north-south section on that line, showing the warm air over the equator, a little bit shifted to the south because we are in January, the cold over the pole. Now, in the we like not temperature, but potential temperature, because air is a compressible fluid. So if I move a different pressure, it will expand and cool because of the pressure. So if I want to take into account that compressibility and making an analogy to an ocean which is incompressible, we're using a quantity which is the modified temperature, which is the potential temperature. So for the purpose of the comparison, today I'm using the potential temperature, and you can still see the cold air and the warm ocean, but I see more the stratification of the atmosphere getting more stratified and warmer going up. And I can see the boundary between the troposphere and the stratosphere, where it's very stratified higher up here. So this is what I'm using, but because it's more a technical talk, I'm going to show you some of the features. So on this left-hand side is a section north-south along the green line. On the right, I have on the left, sorry, I have the sphere, and I can move it and look at the southern pole, the northern pole. And why not clicking on Boston and say, let's go at the edge of that very cold air. And now I can go across the pole and check in the cold air. So this is, you see the section has changed, and I can, I'm moving now from Boston to China across these cold air masses. And you notice that there is this very sharp gradient, which we call the polar front in the middle latitude. Now I can also go and view the southern hemisphere, and I can click on the tip here, and I will cut across the southern pole, and the section will move accordingly to the region. And if you notice, it's actually a little bit less cold because it's summertime for them, and you have still a contrast between the warm and the cold with the polar front around the Antarctic. Now, I like Boston because it gives us a kind of way of talking about something that we experience. So if I'm going back to Boston and superimpose another field, for example, I'm saying, let's superimpose the wind. Now I have the temperature, let's put the wind on top. And the image will get a little bit busy, so the color shading is still the temperature as before, and you can see the cool tone. And on top, I have a wind which is not a strong maximum here. I cannot even read it, but I can change the setting, go back and do, say, plotting every 10 meters per second. And I will see that I have a strong jet associated. So if I'm pulling the jet, the wind is very strong. It goes from 0 to over 50 here. And here is around 40. So there is what we know and we are familiar, a jet stream, a strong wind at upper level, around 200 millimeters. So I can go on the side and say, all right, let's look at 200 millimeters, the distribution of this wind, which is the zonal wind, which is blue. And you notice now that my section is cutting across the very strong maximum now the wind marked in red, which is the over 50 meters per second. So there is a band of very strong wind in the northern hemisphere, the jet stream. This is the level where the plane flies, so you can see the wind swirling around. And on the south hemisphere, you see another jet, but it's not so strong at this time, and this is that one. So the line white here represents the level on which I'm plotting the data. So I'm doing all this to show that the data on this side changes accordingly, and I can go from one to the other. Yes?
What is the dotted line contour? Why dotted?
The dotted line here?
Yeah.
This is because it's changing sign. So if you notice, this wind is positive, it's blowing from west to east, and here it's becoming negative, blowing from east to west. So it's a section you're cutting across. So you're cutting across, let me go back, you're cutting across here, and you see wind blowing from west to east here, and then blowing in the different direction there. So feel free to ask questions. I think it's good, this is not clear. So this is mainly to show the way on the two sides, the section you're practically interacting with the display on the sphere, and making a plot. You can download the image here, but you can even download the data. You can download the data from the section, you can download the data from the globe, and then you can manipulate it in MATLAB, Python, whatever you want. And then you can try to make an image and bring it back to the sphere if you want. And let me show some of these applications. I'm just going to show some of how I've been using it and the main feature that I found in it. So after the ocean, the atmosphere, I have a few examples on the ocean. So I can go to the ocean climatology. And the first things I'm showing to you is the same setup. I have a global field, but because it's an ocean field, it's actually the ocean temperature at the top, at the level of 5 meters, so the sea surface practically is the top level of the ocean, and is the temperature. If I have a lot of land masses, I will do my section is north-south. This section by default is a longitude 0, so at Greenwich. So it's practically cutting across a lot of land. So I like going in the middle of the Pacific and do the section there. So if I click in the middle of the Pacific, I will have a better section because now I span the full Pacific and I'm going from the South Pole to the North Pole along this green line. And the scale here is in meter, but if you notice it's not a linear scale. It shows more on the upper level. But I can switch it off, it's a log scale. I can switch it off, and this will be a normal scale. But if I do that, I can hardly see the wall. You can see the thermocline very much confined in the abyss. So why not center? I can center it on the thermocline, and so I can go up and do a plot in the top layer of the ocean at 1,000 meters. So if I go down to 1,000 meters, you can see the very warm water at the top, and then the gradient of that, and how it's changing going down into the upper. I can also change and zoom in into the abyss and look at the very cold water at the bottom of the ocean. And if you notice the bathymetry of the ocean, is quite a lot of peaks in there, so you can see the variation. But by the way, this data is very high resolution, both in the vertical and the horizontal, and here is a list of all the layers that you can go through. If I go through, we have plenty of choice. Again, just for fun, I'm going to click one of these, and this will be at 200 meters, so if I go at the thermocline, it will be around here at the edge of the very warm water. So the nice things about it, the way I've been interacting with atmospheric data and the ocean data is the same. So if you're talking to students which are getting to know the fields, but they're not really expert on either, it gives them a tool where they don't need to adapt to a different way of plotting or a different convention. You can easily move from one to the other. So we try to stress that analogy. And I also here you will be able to download the data. We haven't got that done yet, but it's coming. So my next step is going a little bit more into, into application, how we interact with the data. And I'm going to show you two examples of computing trajectory, both in the atmosphere and the ocean. So I will now imagine to release particles in the atmosphere and the ocean and look at the trajectory. So I'm interacting with the data at this point. And I'm going back to the here. And I should have the atmosphere, the virtual balloon flight. We call it that instead of releasing particles, imagine I have a set of balloons that I release and they move with the wind. This is showing on this side I have the wind at 250 millibar, and you say to me, where is that? It's because I got the pressure level 250. You will have a better label in the future. So 250 is the wind speed, and it's the same wind that I practically plot, the same level where I plot the wind in my climatology. And this is the wind speed, so it's showing in the red, the very strong wind going from 75 to 100 meters per second. And you notice this is today. This is not a mean. There is more variability in this jet stream. But look it around, it's very windy. It's actually the wind from the global forecast model, and it's starting last night, 7 o'clock last night. And we have 15 days ahead, because we're using the wind from the forecast model. So what I'm going to show, what I'm doing, I'm releasing a set of 10 balloons over a spread of 1 degree of latitude over an area over the US. And because I like to click where I start, I'm starting from here, not far from our region, where the jet is strong. And if I click on there, you can see all the balloons moving. And they're coming together and they start spreading after a while. They're actually spreading. If you look at the bottom, after 4 days, they start spreading a little bit. Let's move it a little bit to be see. And now they're spreading in a row. So one is going towards the tropic, one is coming back to the. So we have a spread on the. If you start from slightly different initial condition, you don't necessarily follow the same path. And this gives you the chaotic nature of the atmospheric flow. You remember, you probably heard the word that of the chaos theory, that you're sensitive to the wing of a butterfly. So it's the moving of the wings of a butterfly. So this is showing a kind of an example. If I just do one particle and I go back here and choose one balloon and launch it, I will have one of this trajectory. And now I'm plotting on that a dot to show you the day. So it's going to take an approximately, I'm going to count in a second and let it go. It started from the US and it's taken it 1, 2, 3, 4, about 5 days, about 10 days to go around the full globe. So it's moving with the jet stream wind and this particle of this balloon around, it takes about 10 days. This is also given us an idea of the time scale of the phenomenon. So the jet stream is moving very fast, but if you think about it, one particle in the jet stream is actually taking 10 days to go around, and it's got enough time to realize that we are on a rotating planet. It's very much influenced from the rotation of the Earth. If you actually notice it's moving from west to east, it's the same direction as the rotation of the Earth. So I'm running it again, and you will see again coming back. I can try now, I would like you to tell me, try another area. Where do you want me to start from? Anyone suggesting? Sahara. Okay, so let's back to the Sahara Desert. And here, if you notice, it depends whether if we are in the wind or not. There is a jet, and it's actually not too strong, but it's not going to the southern hemisphere.
Wow.
And look, it's now gone to Australia, and go around, and it's now putting the back. It's gone even further. So it's got a notice. It's got quite a long distance as well, but not such a west to east pattern, because we were away from the main jet stream. It was more meandering. And anyway, this we can also do 10 balloons, and I'm going to try that. 10 balloons over 10 degree, much bigger spread, and you will see more when the trajectory, the spread of the trajectory. So if I start from Africa, from the Sahara, some will go in the northern hemisphere and some will go down in the southern hemisphere. So showing you that it depends whether you are within, not very far off to start with, but depending on that. Okay, I think I have to move on. I'm going to move back to the oceans and using ocean particles. The ocean particles here are the same concept. I'm clearing out the image. And I have a wind, not a wind anymore, I have ocean currents. And they will be at the depth of 5 meters. And I'm going to show that, imagine I release, there is plastic going into the ocean. So I'm going to make the analogy, not of a balloon now, there will be plastic, another object of plastic going into the ocean. And that can be released along the coastline of the Atlantic. So if I click different point where the plastic come in, and then from the coast of the US there will be even more coming. And then I can move around and put a few more dots coming from the west coast, a few more coming from the Japan and the East China. And now I've started, what I'm computing is now, if you notice here, I start from this point. This is 1 month. After 1 month, the plastic is here. The white dot is 1 month. Red dot is 1 year. So the currents are much lower than the wind in the atmosphere, so you're looking at much longer time scales. But the interesting thing is that all this object that we have released close to the coast, with the mean currents, they're drifting into the middle of the Atlantic. You notice? They're coming. Now it's about, if you know, can be used in other fields, and how you can use it, for example, socioeconomic data as well. And so Glenn is going to present this part and try to get you engaged also if you are not in Crosswell. We take question then.
So I'm going to talk a little bit about some of the technical aspects of this as well. Vika has been showing a version of this, which is kind of intended for courseware. So the idea is you have the globe that you've seen, you have the right-hand side, and you have a set of different modules which can all be put up, and in some ways, at some points, can cooperate with each other to make something that has a sort of a coherent set of information. For example, in what she just showed, in the plastic, you can go to the menu and find either simple kind of queries, where are you? And so you could ask, where is this aggregation? And you click and it shows you latitude, longitude, that information. Or you can go instead and try and annotate the figure. For example, you can say, I'd like to kind of highlight certain spots. Here, because these are where the main aggregations are, and then I can go back to the menu and say, let's turn that in and make a map of it that I can put into my report or my class demonstration to show you. So these are just 3 modules which are interacting with each other to use the same kinds of information and pass it back and forth. So that's one approach. We are also working on some other approaches, and these are intended for people to both experiment a little bit or to go ahead and incorporate it into your own courses. So the first and very simplest thing is if you have an image and you want to see what it looks like on the sphere, you can do that with the existing website. Images look like this. They're what's called an equirectangular projection. They have equal steps of latitude, equal steps of longitude, and so the Earth picture looks like that. So if you have a picture which looks something like that, you can go to the ESI site, EsGlobe ESI site, and you can type in the URL of that particular image. In this case, this is one that was prepared for the library. You click on it, it brings it across the network, and it shows you. This was where books have gone out and where they came from back to the library during September. We had the physical sphere over there. So that's just an example, but you can basically put anything. There are some limitations on movies in MP4 format. The software underneath this, which is called P5.js, was originally developed as an artist tool. I think maybe architecture.
It's the web version of processing, which I'm sure people have probably used processing in the developed at Media Lab.
And so it has some restrictions on MP movies, but most of what the movies we've shown, or what we showed originally were MP4. So I will show that later. So that's the very preview. If you have something you want to see, well, what does it look like? Then you could use it in the class, because once it's on the sphere, you have all the same ability to move it around. So our next version is to say, what we've really developed is a set of libraries. You can pull those into your own HTML pages, the web pages, and then use those. And I want to show an example of that on the work that John Marshall and I are doing for physics. So this is a case where there's just a web page, and I will show you actually the code in a moment. We brought the sphere in, and when you have it, you have the ability to manipulate it. And what this is intended to show is to illustrate the Coriolis force. So if you have a non-rotating Earth, and you have a very slow satellite moving over it, the pole, this is the track. Now think of the Earth rotating underneath that track. And the satellite is sending down a signal that makes a little red mark on the Earth underneath it. And so let's look at what that looks like if we do that. So you see under each yellow dot, there's a red dot just appearing, and then you have the track where the satellite went. And you see it's curved. If you're sitting on the Earth, you see this curved track to the right, that's Borealis. That's, in some sense, all it really is. It's a lot more complicated when you do the math. Now, as Latika showed, the particles in the Earth move around. So we've seen one effect, that if they're moving this way, there's a tendency to try and deflect that way. But the other effect on the particles is the pressure. So this is this is an MP4. In fact, of the pressure, sort of read that at the bottom, it's actually showing what's going to be displayed. This shows how the pressure field evolves. Or it's really what's called the geopotential height, which you could think of as a surface, and it wants to try and go down that surface, just as if you put a ball on a hill, it wants to roll down the hill into the pole. So there's a push this way, but then the response to that is because of the Borealis force is that it moves to the right of that push. So if we go to this on top of this map, and we take a spot on the map, for example, here on the west coast, and again launch a virtual particle. This shows the trajectory of that particle, and you can see rather than going down the pressure gradient into the pole, it's going around, because what you're doing is you're balancing the force, and the Borealis force is trying to push you in the other, turn you to the right. So this is an example of we think we are going to be using it this fall in 801, the first year physics course. And this is what it looks like in code. So if you're familiar with HTML, you can read it, but basically there's a section where you bring in the various P5 modules that do the graphics and the R module that gives you the sphere. And then there's a function that's executed. Let me skip that and come back to it. This is the main body, the text, and there's a set of references. That's what the web knows, is to put this little line and say you can click on this, which say orient the sphere, show this movie, show that movie, show the geopotential height movie, and then run the trajectories. And then the back, like the back one, is saying there is a function that you put in that says, if you click, I'll tell you what the latitude and longitude is, take that latitude and longitude, feed it into a program to calculate the jet. This is all of the HTML that went into that page that you received. So it's two rather large type pages. Now, in order to do these, you need to have something that's doing computing. So you need to have a back end, sort of hiding underneath that says, okay, here's my latitude and longitude, now I'm going to compute and make these images of what the balloon looks like on top of the Earth. So when you have something that is doing more than just showing movies or images, you need to have something then that can run scripts, run programs, and tell it how to create a new image. And those scripts can be many forms. We have examples of all of these, but we use Python commonly, MATLAB or Octave, C programs, basically anything. The nice thing about doing this on the back end is that it says when you construct a back end, you know your data, you know how to extract the information from that data, and you know how to make a picture of that data. So it's not really sensitive. It's not as though you have to have data in a particular format. You just have to be able to accept a set of arguments about what the user wants to do with the data and do it with the data and your programs that you're already used to using when you have the data sets. So what you've seen today, data, some of it was stored in essentially MATLAB files, some of it was stored in Python files, some of it was stored in what's called NetCDF, common data format. And we also have other forms of spreadsheets that we can use. I'll show you examples. So this is a spreadsheet from Gapminder. I'll show you the example shortly, but this is what it looks like typically. Country, whatever the data set is, versus country and year. This is just part of that data set. So that's kind of natural. So let's go look at that example. So this is an example of social economic data. So this is from gapminder.org. Used quite a bit. This is a list of the data sets that are available on there. It's a very partial list because if you go down to the bottom, you can see that there are 519 different data sets that you predict. And all of these are basically the same thing. They're country and information by year. Many of them, unfortunately, are not very complete because they rely on the reporting countries to report. So what you can do is you can go to that data set, you can pick out one that you want, and just copy the URL over into here, using the default, download, which goes and gets the data from Gapminder, prepares it, and then you can begin to explore it. So we can explore that data in what is called graphical information system variety, where you say, I'd like to know what this particular data, which is again labor, was in a particular country. Click on the country, you get the country, you get the time distributed. In this case, the labor force fraction. Another country, Italy, Rica, you can see lots of variation and kind of up and down. Or Algeria, you can see a systematic improvement there. Maybe someone knows why. Or the U.S., you can see the minor recession and then the sort of major drop late in 2000. So I want to just go back and point out two countries here, Algeria, that one, and Tajikistan, which is here. And the reason I'm pointing these out are these are ones that have fairly large changes. Because what I want to do now is to show the same data set, but as a movie on the sphere. And so the changing colors represent the changing values. And the reason I point out those two countries is if you look at it carefully, those you can actually see substantial changes in Nigeria. Going from red, which is not so good, to yellow, which is a little better. The little tiny Tajikistan over here by the Caspian, I guess. You can see sort of it goes up and down. Look at it carefully. The movie also shows the date in rather small letters. This is one example of using that data. It's probably not the world's greatest visualization of it. And so somebody who's interested in playing with this could say, I can figure out a better way to show the same information on the sphere. But that's part of what we're trying to do, is to make it available. That was about it. I just wanted to comment. You may have seen the advertisement for this. They have a picture of a physical sphere. We do have physical spheres in this compartment, a 2-foot and a 10-inch from the EsGlobe company, and they can show much the same data and have much the same software and interfaces, so it's possible to show the data on a real sphere where people can walk around, get a sense of a sphere, and then come back and they can work with it instead of on the virtual sphere. So I just want to finish with a brief summary and statement. This again shows a movie of the radioactive material from Fukushima, a rather disturbing movie, showing again, as Monica emphasized, it doesn't take very long to get around the Earth. The Earth is a connected system. We are seeing the dust from Africa, we're seeing the radiation from Fukushima. So just to summarize, we've been testing it in 12307. Plan to use it in 801. It's ideal for visualizing global data sets. This is just an example, not visible. And you probably can't read. This data was pulled directly off the net right now. I found an image. Actually, I found, yes, Bridgewater State found the image, and then I refound it. And I basically put that in and said, show that image. Right off from the hematology.org. Hematologic.org. So it's possible to show all kinds of data. This is data having to do with malaria. And you, of course, don't have to just show Earth data. Show planets as well. Jupiter. Some of the other planets are pretty dull. Mars was. And finally, we hope that people will be interested in using this in courses or talks or outreach events. And please contact us. We'll be glad to talk with you and glad to work with you.